I am going to try today to sort of give the philosophical wrap-up of the whole gluing discussion and get us motivated for thinking about these abstract regularization approaches. So at some point I may or may not go back and talk about how the sort of transversality part of the geometric regularization works, but that is also something that at least we did in an example last semester. And so the upshot of this whole discussion of geometric regularization is that the analytic key parts here are an equivariant transversality, where the key tool is really a Sartre-Smith theorem, and this gluing construction, I guess, with a key tool that we used, and tool, beyond actually hard analytical work, is a Newton iteration that we can, quote. So those are really the biggest pieces that you can quote there. Everything else kind of needs to get done by hand. So one motivation right here is that maybe we would like to do less things by hand with every new holomorphic curve moduli space. We would like to not have to boil things down to a Sartre-Smith theorem and a Newton iteration. So we'd like some bigger scale black boxes to work with. And on some level, the literature has been doing that by just sort of quoting the convex span of ideas in papers. But that's, we should make that mathematically rigorous. That's one idea of this abstract approach. We'll talk about other ideas, and then there's a core ideas of stabilization that I sort of talked about briefly last time, and I need to talk about this because I want to tell you what gluing is going to be in that setting, though I'm not actually going to do this. So before I get there, here's somehow the abstract script that you get when you try to run one or the other stories for a moduli space. And so this is what I talked about a whole lot. The compact moduli space is some set of holomorphic curves, modular reparametrization, and then you glue in some broken or nodal curves. So that's really the right way of thinking about it when you do geometric regularization, because step 0 is Fredholm description, in this case, of that piece here. That means, right, you need to later on still quotient out. That requires some equivariance in the transversality. And once you have this equivariantly transverse, you can quote a quotient theorem to get a smooth structure on that. And then you need to somehow glue in the broken stuff, right, and make this compact. So. And then finally, you need to convince yourself that whatever choices you made here don't really matter, on the level of counts or homologies or infinity algebras that you get out. So one of the complaints also was that step 4 usually requires you to run through 0 to 3 another 2 times, just slightly different settings. So abstract regularization sort of convincingly only consists of 2 steps rather than 4, of course differently numbered. But the point in putting them side by side is also to see how things really sort of map to each other. So this whole compactness thing here really is something that you have to start off with in the abstract case. Because in the abstract case, really our goal is to write the compact set as some sort of 0 set. So we need to start with a compact topological space, and that's where Gromov compactness comes in. And we don't need all the gluing. We kind of just need the pre-gluing, or maybe not even the pre-gluing, because we really just want a topology there. So that's a lot softer than the Newton iteration. then we want local Fredholm descriptions, and we need to understand how they fit together. And that together should make sense of this, writing this as S inverse of 0. And then we would like some kind of regularization theorem for sections of that type. Let's say, you perturb them, you get something out that has a fundamental class, and the fundamental class doesn't depend on the perturbation, essentially. Of course, that, in what sense that is true depends on what sense of a section that is. So, what the beauty here is that this step here should be a completely general fact for a certain type of section. Well, I'm going to put that in quotation marks. It's not clear what kind of bundle and what kind of section. Step 0 also we usually know. There's sort of no sense in which we can even get started unless we have some kind of compact space of curves that we want to deal with. And so all the hard work really lies in these Fredholm descriptions and transition informations. And so let's see what goes in there. On some level, sort of the bit of the Fredholm thing here, together with a little bit maybe of that transversality, will usually get into the finding local Fredholm descriptions. Gluing is going to be also used to make local Fredholm description near nodal curves. And right, oh yeah, we also need to quotient. That's also part of this whole sort of description, right? Near a single curve. We needed a local slice to the reparametrization action. Right. So all of the analysis that happens here sort of goes all into point 1. And we don't really see anything that tells us how to do 1 prime, the transition information. So except for somehow knowing that there's a global description on the level of holomorphic maps. So that's something that one should be worried about. And it's, one of the good places to ask whether theories are complete is whether that's actually done. Right. And however, if we can get this analytic piece done, right, then we don't need ever equivariant transversality. That's the beauty. And all of this work here, which cycles through this twice more, is just done automatically. So that's the first pitch for why abstract regularizations. It should be somehow not just easier, it should also be more transferable and quotable. And when I say more general, I mean, I think there's also one good question to ask of an abstract theory is that what if your d-bar operator is already transverse? It should also give you, a setting in which to think about, the compactified moduli space. So, if you happen to have a regular J, your abstract setting should also help you to just, organize the whole gluing discussion. So, good. But the other big reason really is that we don't usually have regular J's. So, little language here, right? So when I say a regular J, what I mean is that the d-bar operator by itself is transverse to 0. And that will always be invariant under automorphisms under the reparameterization action. So you're asking for equivariant transversality here. And the rough rule of thumb for the rarely is that you kind of need to be sure that all your curves are somewhere injective. Where the meaning of somewhere varies with the symmetries that your problem has. So, and the reason really why sometimes we can find regular J's in perceivedly large sets of problems, like all exact manifolds or all monotone manifolds, is that we can drastically reduce the symmetry. For example, in those cases we can exclude bubbling, hopefully, and so then we never have to work with the whole Möbius transformations. If we did have to work with those Möbius transformations, we usually toast because we can't get that much injectivity. So, right. So, as ammunition and thing to just keep in mind is, what are a couple of typical obstructions to finding transverse J's? The first and sort of historically most well-known one is multiply covered spheres that in general also are not necessarily a problem, but when they come in the wrong Chern number, they are a problem. So let's see. Let me start with an injective holomorphic curve. Well, call that image a curve that's actually a submanifold of M. But now I could, parameterize K times that curve by just precomposing with a multiple cover of the sphere. So I'm going to take Z to C, K. And I'm going to call the whole thing here U sub K. So let's see, right? So if my D bar was transverse, then
wait, but these curves aren't multiply. These curves aren't somewhere injective. Correct?
Indeed.
So then
we're going to
wait. Are we worrying about obstructions when all the curves are somewhere injective? Is that what you're trying to say, or no?
No. Well, I told you that having somewhere injectivity usually guarantees finding regular J's. And now I want to give you examples where not having somewhere injectivity indeed obstructs finding regular J's. So, you could think that, maybe you just haven't been smart enough in proving that there's always a regular J. So I want to.
I thought because you circled rarely, you're explaining that when there's some. Oh.
But I explained the rarely.
Oh, right.
And now I'm going to prove that there is something in the complement of rarely. So, right. So, if my d-bar operator is transverse, then I know what dimension to expect from our standard test space of genus 0 with 1 point, right, in class A with complex structure J, namely my Riemann-Roch gives me 2n plus 2c1 in the class A, and then I quotient out by everything here that keeps infinity fixed, so I get to subtract 4. The exact constants are not important. What is important is that the Chern class here comes in with, a positive factor. So now let's see. The thing here is that, let's see, the C1, right, and let me assume here that C1 of the curve C, so the tangent bundle on C, is -1. And I would like that U to actually be transversely cut out and to exist. So I should better make sure that that's possible. So the dimension here of this space that U lies in, I'm expecting as 2n -2, -4, -6. Right? So just for fun, let me say maybe these are actually isolated points now. That seems strange. Oh yes, the spheres will be isolated, and then I move the marked points around and evaluate, so I'm going to see two-dimensional sets that spheres can go through. So when n is 3, I'm going to see a zero-dimensional moduli space here, so the assumption is that there is no reason for that U to not exist. Right? And there are examples of these guys. So that exists, but the problem is once U exists, all the UKs also exist. Right? So that means there's a moduli spaces of k times that class, which are clearly not empty, but their expected dimension will get smaller and smaller with larger k. So that will get less than 0 for pretty much no matter what dimension we were in if we take k large enough. So that is sort of the first way in which one understood that, while this making things transverse with J is awfully nice, there can be cases where, just sort of this automatic existence of multiple covers will just, contradict transversality in, higher degrees of multiple covers. And that's exactly, the place where we would awfully like to break the symmetry of having this J here maybe depend on the base point in P1 a little. Right? Then we could perturb these moduli spaces separately and make them separately transverse. Well, no, that's a lie. Right, then this automatic existence doesn't work. Right, yeah, so being able to cover with this here would mean, right, that so if my J depends on the point in P1 and this cover doesn't preserve that, then I would be breaking the symmetry, and hence I don't have this implication. And so in fact, if you then go through the proof, you are actually able to find transverse J's with your Sartre-Smale. But sorry, let me finish that sentence. Bubbling somehow forces this symmetry onto us, just because the sequence of rescalings are that gives us a bubble are not uniquely chosen. And so in the limit of Gromov compactness, we have to forget about them again. And so whenever spheres occur as bubbles, we have no choice but to work with domain independent J's, because that's what naturally appears. Okay,
And
question.
if you tried to use a domain-dependent J, then that would be breaking equivariance, right?
Right. Yes. That. Yeah. Exactly. Right. Good. So this is a very convincing argument, and it already. Why are my numbers? There's several numbers 1 here. That's not terribly good. So number 2 already says so. This obstruction to transversality occurs in almost all moduli spaces, in almost all symplectic manifolds, e.g. as soon as bubbling can't be prevented. So, well, I would need to rule out bubbling with negative churn. Numbers. So if I can outrule that, fine. And sometimes that's possible by energy arguments, which sort of boil down to sort of exactness or monotonicity. And a lot of the manifolds that you see will be exact or monotone. However, I challenge you to make a measure on a space of symplectic manifolds in which the set of exact or monotone symplectic manifolds does not measure 0. So my claim is that the random symplectic manifold will always have negative churn bubbling, and so need to come up with some other ideas to regularize. And even if you decide you really just want to work in exact symplectic manifolds, there's argument number 3 that says, well, some moduli spaces you can do in exact symplectic manifolds, but there are evil curves as soon as you try to do something like contact homology. So that example is it's always sort of the cover problem. So here I'm not going to start and try and say what contact homology is. There's an odd dimensional manifold and a contact 1 form, and now there are somehow there are trivial solutions that are not constant, but that are constant except for an r direction. So that's a cylinder here that sits in r times y with a j that is r invariant and in some good ways compatible with the exact symplectic form that you get from multiplying e to the s, where s is the r variable on that contact form. So the form of these cylinders is that it's simply stays constant over a Reeb orbit. So the second component here in particular does not depend on t, where gamma is just a loop in y. It being a Reeb orbit and j doing something that pairs the Reeb vector field with the r direction tells you exactly that this is going to be holomorphic. So you have the same sort of situation where this thing is holomorphic and always exists, no matter what. And then you can do problematic things by just taking a branched cover of the cylinder. Yeah. Any J-holomorphic map. I'm not going to go into discussing branched covers, but you can imagine again, situations where, okay, these guys exist, they exist transversely, all is fine, but depending on the type of cover here, that stuff is just supposed to not exist. So they always exist. But we cannot guarantee that they get cut out transversely, because that would have to come from here. So that's something you have to deal with, even in exact settings, if you allow yourself cylinders of that type. One more sort of side story here is that somehow historically people first knew about multiply covered spheres, and well, they have two features. One feature is that they show you that transversality doesn't always work, and the other feature is that they have isotropy. So there's a finite symmetry group that will fix this UK, which we'll get to next. And so somehow that got mixed in people's minds, that somehow transversality problems happen when there's isotropy and vice versa. However, there is that example of disks, which I sort of always try to make clear that disks sometimes will be nowhere injective, but also have no isotropy. So, if you don't believe that, or want to see something funky, ask somebody about the lantern example. That's a nowhere injective disk which has isotropy, trivial, or no stabilizer. And that's an example where you have transversality problems, although you have no sort of expected orbifold singularities. So, and that's argument number one, why I'm going to very soon just not talk about isotropy anymore. Question.
So did anyone come up with any sort of geometric, not abstract approach in situations where you have like problems because of multiply covered spheres?
Yeah, so there's Chilibak, Mohnke, and also Parker have this approach where you try to find sort of a global hypersurface that you use to stabilize your domains. Right, what we did was we sort of used hypersurface to stabilize it, or to find local slices to the automorphism action. But that always just sort of worked locally in the neighborhood of a curve. So if you use the right kind of Donaldson hypersurfaces, they're sort of guaranteed to intersect all your curves in your entire moduli space, transverse in the right number of points. And so essentially the idea is to use that to make a global local slice. And then you're working on that slice. The different point of view on that is to say I'm going to make my J depend on the points where that intersection happens. So in that sense, I would call that still sort of a geometric approach. Because it gives you equivariant transversality and also very heavily depends on understanding the geometry of your curves. All right, and there are hopes that might work with disks and higher generality, but again, you have to just like with every geometric approach, like every time you change your problem a little bit, you have to go through the entire theory and make sure everything still works. Okay, so that's the why of talking about abstract things. And this is very much on the holomorphic curve side, and now I'm going to switch I'm going to brutally switch gears back and forth today. So, well, maybe one day it'll keep you on your toes. Right? So I need to talk about stabilization because I then want to talk about gluing again. So, and I think I had that on the board briefly last time. So we'll just get us back into our setting. So what I argued from sort of these local hypersurface constructions was that most of your moduli space, at least not near the smooth curves, we can actually write, we can restrict the d-bar operator, so that would be our sigma here, to a local slice. So B will be maps that go through hypersurface at some point. That will be a Fredholm section, and then the zero set is in fact locally homeomorphic to some space of my holomorphic curves. Here, if I have isotropy, I might have to quotient by that the finite stabilizer of my curve. But that's something that we're not so worried about, because if this is a smooth manifold, that's a finite group. This is still something like an orbifold chart. So you can deal with fundamental cycles and orbifolds. Right. And now except the problem is, right, in general, that is not a transverse section, and so this zero set here has, a fuzzy, as a topological space with no smooth structure. So we need more to get any mileage on, regularizing M bar. And so the first idea here was to sort of just look at the bundle of co-kernels, right? So of every zero, I'm going to look at the co-kernel of my operator there. And if I'm lucky, that's a bundle. In general, it has no reason to be a bundle because the dimension of the co-kernel can jump. So then you might try to somehow enlarge uniformly, your fibers here to sort of make things fit into one finite dimensional bundle. And locally, that's essentially the same as trying
due to lack of activity.
Stabilization. So the notion of stabilization is to find, you could say, let me find a representative of this co-kernel here, namely a finite dimensional subset in my bundle. And then, it needs to cover the co-kernel, and if it was a representative of this, this would be a direct sum here. But in this setting here, I could take this finite dimensional subspace larger. All I need is for it to cover my co-kernel. And that way, it can work in a good neighborhood. So once I have transversality at one point here, I will have that in a whole neighborhood of this is like, what this says here is really surjectivity of the differential of this map here. So if to my section B going to sigma of B, I now just add vectors in that finite dimensional subspace E. Exactly this sum here says that this is a transverse section now. Since if I have a transverse section, I get a finite dimensional manifold here. So the zero set of that space here is finite dimensional, smooth, usually, manifold. Right, and strictly speaking, it's the pairs B and E, so that d bar B is plus E is 0. But really, what we're thinking about here usually is that this is usually holomorphic curves, for which d bar U then sort of lies in this finite dimensional set. And I know what this is because this here is my E, or minus E. So I can identify that. Right. And yeah, now somehow the zero set is exactly, the original zero set is exactly those pairs B and E where E happens to be 0. So in that language, the section that I still need to look at is this very simple map, B comma E to E. And in this language, the remaining section that I need to look at is simply D bar, which gives me E, or minus E in this case. And this is exactly the sort of translation to the finite dimensional reduction, right? So the remaining there's a finite dimensional base manifold here. That's this U. This here is capital U. Maybe. And I have this finite dimensional bundle over it and a section in it, and so the zero set of that nice smooth finite dimensional section now gives me a piece of my contractified moduli space, hopefully. So the finite dimensional reduction is something that you may or may not want to do, depending on your taste for how to do abstract regularization. But somehow this stabilization sort of essentially happens in all theories at some point. That's just, it's a sort of an equivalent way of saying this section is Fredholm. Is to say there is a space that if I add this extra finite dimensional set of perturbations, then the zero set becomes a smooth manifold. I think, strictly speaking, I could probably prove that that statement is equivalent to the section being a Fredholm smooth. So, good. And sort of also there's sort of a rough philosophy here of, if I have these kinds of descriptions locally, what should maybe locally be a piece of my fundamental class of, oops, goodness, that looks bad. I want sigma. Right, so I have this very irregular zero set. I would like to make, at least locally, a piece of fundamental class. In this setting here, before I've made this finite dimensional reduction, before I've renamed things, what I do have here is a bundle E over a manifold. And those things have Euler class. And I might just want to try and take the Euler class of that bundle. And then we might remember that Euler classes can be defined by perturbing a section and looking at its zero set. And so in this world here, really, I ought to just perturb my section to make it transverse. And look at that. So right, and then there's, just for those who are worried about what happens with the isotropy, right? So this might still be invariant under some finite group. And then essentially I ought to just find maybe a transverse section here, and quotient by that finite group. If we're lucky, then that looks like an orbifold, and maybe that has a piece of fundamental class. Question.
So this Euler thing seems kind of weird, because it seems like it could be that in each local piece, U is contractible or something.
Right. Yeah. So that's why this says philosophy here. Right. So you need to, of course, find some way in which these Euler classes are well defined up to something on the boundary and near the other charts, and so really, I mean, you ought to sort of sum the Euler classes in some way in which the classes actually sort of patch up to something nicely. So, yes, but quite obviously these are trivial bundles here as I've written them down, so they have no Euler class. So all the topological information comes from how these whole charts sort of will patch together. Yeah, I mean, the main bit of philosophy here is that once you have a finite dimensional situation with a section, you can either think about an Euler class or you can perturb. And personally, I think that's sort of essentially the same thing, but some people like to insist that you ought to go one or another way. So now that we have the notion of a stabilization, I can tell you, right, so this is a game that we can play already, in the part of our moduli spaces that is not broken curves, right? Because we know how to make the finite, we know how to make the Fredholm sections, and then we could go through this general setup here. The question is how to do that near broken curves. Right? So, again, how did we actually do it near unbroken curves is we found a local slice to the automorphism action, and then we simply restricted our d-bar operator to that local slice. And so now, sort of in the abstract world, most approaches will first stabilize and then glue. The polyfold approach somehow does something completely different, and that's what I'm going to talk about that later. And then we can talk about whether maybe we can reinterpret that as gluing after stabilization. So, let's see. So first I'm going to go back to saying, I did describe the broken curves as fiber products. So let me take a broken curve, I'm just going to abstractly think of a pair of curves that might be two spheres that have a node or two Hamiltonian Floer trajectories with a common limit. So each of these is an unbroken one by themselves, and so I can write each of these as locally the zero set of some Fredholm section. And then I can identify a neighborhood within the broken ones as sort of a product of neighborhoods here, except it's usually a fiber product, so there's something going on, for example, fiber product over the periodic orbits in Hamiltonian theory. So that by itself is not so bad. That's a fiber product of Fredholm sections, you'd think. You can write that as a Fredholm section again. However, that's just the neighborhood within the broken ones. I do need to, say how this sits within the whole compact moduli space. So, right. But before I do that, I'm going to going to write this also as the zero set of some nice section, which I'll get after stabilizing. So the reason I want to stabilize is I want to get myself into a situation where things are transverse, because that's where I know how to glue. So let's see. Right. So I should maybe remind you what this in the Hamiltonian Floer case. There's the base space here actually are slices, and well, what are these slices? They're somehow cylinder maps which have some limits. And then we need some kind of slicing thing. Usually there's just an R action on this. So just to get ourselves some visual, I can fix one parameter here. And so the one parameter that I am going to fix is that on which level within R I'm going to intersect a hypersurface. So I'm fixing that S equal to R. That's how I fix my shift. I don't necessarily have a control of where along the circle I'm going to hit that hypersurface. But that's extra geometry here. I just wanted to have some visual here of what the slices are. And then over that I have my bundle of LP sections. Right, and so from here to there I now have my section, which is my the d-bar operator, usually with the Hamiltonian perturbation. Okay. And stabilizing means now that I have sort of combined transversality of the d-bar operator plus this injection here. And that means I ought to be able to write this zero set here as something, namely, so here's my bundle, just E minus times E plus, over, the broken trajectories up to E plus and minus. So these will be pairs B minus B plus. And then I also want to keep track of E minus and E plus. Right? And I should have this the d-bar equation of B plus and B minus is true up to this error E plus and minus. Right, and then the section here simply is the one that maps this whole tuple to the pair E minus E plus. That is a very silly way of saying that what the holomorphic curves are here. What I didn't also encode here was this fiber product of the periodic orbits. And so here I'm implicitly assuming that the B minus and B plus already match at the ends. Right? If this were nodal curves, I would have to just add some finite dimensional thing here and sort of write into that the equation that, v minus at that point is equal to v plus at that point. But that's going to be more Fredholm stuff, and it's going to be more Fredholm stuff, and this is going to be still smooth and finite dimensional here. So if it's, this base is, so this is my finite dimensional reduction here. But I want to focus on the stabilization because, so what I have here is stabilized sections. So those go from the slice times E plus minus to curly E plus minus. And those will then be transverse to 0. Okay. So, so this set down here I can think of as the pair sigma E minus times sigma E plus, and it's 0 set. A whole lot of rewriting of the broken trajectories, and what I would now like to do is I would like to actually glue. So and the claim is that the sort of generalized gluing map that I ought to use now will look very similar to the gluing map that we used for the d-bar operator, except I'm taking the broken curves. Oops. So I'm taking the sort of perturbed broken curves right, so this is a nice smooth finite dimensional manifold of broken curves that are holomorphic up to E minus and E plus, and I'm going to try to glue them to something with some gluing parameters. And well, what am I thinking I'm going to get? Well, I'm going to get, when I glue this stuff, and I'm going to obviously I'm going to glue my maps together, so I should get some maps that are near the glued one or pre-glued one, and that d-bar operator on that map should be near the d-bar operator on the pre-glued one. Well, the pre-glued guys sort of have an E minus and an E plus on the right-hand side, so I'm going to get some error on the right-hand side, and the hope would be that there's an analogous to pre-gluing on the perturbations. So that's pretty fuzzy here. Right? The main thing is, there's a Fredholm problem here, really, there's Right, there's a transversely cut out set of broken things that satisfy a PDE. I've just now added this finite dimensional E stuff to that PDE, but it's a transversely cut out thing of pairs, and so I run exactly the same kind of analysis that we did for the actual transverse gluing, and make maps nearby. So, and then I have to figure out in what sense to really say what they satisfy. But the analysis is exactly the same, making the gluing map and then also proving local injectivity and surjectivity. The only problem is to say what that space here actually is. But I can on some level sort of forget about what that space really is, because then I can, once I have this gluing, I believe that I have a gluing here, I can then look at a proper neighborhood within my whole compact moduli space. And that will then be, well, the actual holomorphic curves in here together with the actual holomorphic curves in there. And I can, the virtue of this gluing map here is that I can now think of them as sitting in the same space. So that will then be the zero set of these perturbed holomorphic broken maps times a gluing parameter, where I now allow myself infinity, and what sits over here is simply E minus and E plus. That's a silly sign. This is a, of course I should write this here also if it's a bundle, right? So this is the trivial bundle where E minus times E plus is the fiber. So, right, so what is the section here? Right, at infinity, that section is simply the section that I had up here. So that's, I call this S infinity, then at infinity. This is going to be S infinity, and at over R1 infinity. All that I should do here is, right, I'm here looking at a point in that space, so that would be a point, a pair, V comma E, of course lying because there should be equivalence classes and everything, right? What I know is that D bar, D bar of V is equal to my E, and then I ought to be able to somehow write my E as a pre-gluing or gluing in some sense of an E minus and an E plus, because that will allow me to map this to this fiber. So you can imagine that, whatever this pre-gluing of these perturbations is, if I glue 0 to 0, I get 0. So this kind of silly section here ought to really cut out the truly holomorphic curves from this bigger gluing map. So, right, so there's no reason why this section now ought to be transverse, but it's a smooth section in a finite dimensional vector bundle. So not only did we get a local Fredholm description, we actually got a local finite dimensional reduction. So, semi-obvious issues with it is that I've, of course, severely waved hand. Let me point at the places where that hand waving actually is a bit of a problem. Obviously, I need to make sense of pre-gluing. And that means somehow that my vectors E minus and E plus kind of have to actually live over the cylinder, and I'm supposed to be able to sort of shift them over each other. That's not so bad. I mean, they are, after all, elements in this LP space here. However, the other thing that I'm supposed to be able to do is, from this preglued one, I'm supposed to be able to read off E minus and E plus. And I would like the zeros of this section to not just be holomorphic, but to also be the only holomorphic curves and the unique holomorphic curves, or to not occur several times. So let's see, right? So what I don't want to have happen is to have non-zero E minus and E plus that preglue to something that's zero, because that would be, let's see, that would contradict one of my requirements, right? There would be something going on. Oh, right, because then one at the same holomorphic curve, right? So V could then come from from V 0 0 and from V E minus and E plus, where these are non-zero here. Right. Yeah, so, sorry, but the points in this space here really are still pairs V minus, V plus, E minus, and E plus. So the same holomorphic curve would actually appear twice in these zeros, and that would screw up my count. Right? So that means I need to somehow make sure that these little abstract perturbations are actually somehow supported in the domain where I don't want to preglue. Right, so that they're just sort of bumps that I shift apart. So essentially what I would call this is sort of a somewhat geometric perturbation scheme. I need to sort of actually understand what's geometrically happening in these constructions. And the other thing is that there's also a differentiability problem here. Right, so the first point was I want this pair, or the pregluing, to sort of be injective. And the other thing is that I have a little bit of a differentiability problem with shifts. Right, so think of E plus minus as a section, really, that sits over my slice. So right, so pretty much, well, I've picked one vector over each point in here. Right, so that's what I want to think of here. And that somehow ought to give me a smooth section in the preglued thing. So I ought to be able to take pairs in the slice and the parameter and somehow get into my large space here by somehow mapping V minus V plus R to, well, so what? Right, so E minus at that base point, which would be V minus, except we're going to preglue, so my V minus is going to get shifted. And then E plus and V plus, but that's also going to get shifted. And so, again, I have this problem that if V minus or V plus is not a smooth map, and I'm allowed to vary R, then this is not necessarily a differentiable map here. At least so. Right, so this section here is now a composition of two things. It's first the shift map and then applying this E minus E plus sections. So if I allow myself just any odd section here, there's no way that this is going to be a differentiable map on a Banach manifold. So really, I need very special forms of sections for which this construction here is smooth, although it factors through something that's not smooth. So I need this differentiable sort of despite the failure of this map here going to shift. So, fortunately, in the cases that we care about, there seem to be such sets, and I'll try to explain that at some point. But that's somewhere in the nitty-gritty of the analysis that one does to, get these finite dimensional reductions, and that's again sort of goes somewhat against sort of my hope or requirement that one ought to not have to come up with new ideas every time there's a new moduli space problem. So here there's one place where you need a new idea of making sure that stabilizations interact nicely with the pre-gluing. But short of that, this is sort of the winning strategy here. So and it's also, this is a similar problem really that we're going to see also for the transition information. So, and we've already seen this problem when we did the local slices. So these are not terribly new, and somehow the analytic problems here can be solved in the same way that we're going to solve them in the simpler settings. So this is not a problem of gluing here, this is a problem of just making a decent setup to begin with. So, so that was the answer to what do you do near nodal curves. Right? You glue. Get yourself in a transverse situation and then you glue. So and there's issues. So now the same issues we're going to see again when we start thinking about the transition informations. So now I've decided to properly go into a test case of holomorphic spheres, of a fixed homology class, where I'm just cautioned by things that fix infinity. Right, in the back of my mind, I do that because I want this evaluation map to be well defined. But that's not. I'm not going to be worried about the evaluation map right now. What I am worried about is how these different Fredholm descriptions kind of fit together. So here's one local slice where I've used hypersurfaces H0 and H1. Here's another local slice where I've used H'0 and H'1 as local slices. And now I can take 0 sets of my d-bar operator in each of them, and hopefully, I've taken them small enough, they give me local homeomorphisms to my compactified moduli space. And now obviously I should be looking at some transition information that I get between these. the problem, or weird thing here, is that, right, this is a Banach manifold here, this slice, that is also Banach manifold S prime. You know, and the zero set here is a very fuzzy but very small little subset of that. So this transition information, or the transition map, is only defined on this very small fuzzy little subset, naturally. How can we remedy this? Well, there could be that vague hope that at least on some little piece, this compactified moduli space sits in a space of maps modulo automorphism, right? And our two slices sit in there. Or, local homeomorphism state. Right? The problem with that is that the transition map is not cool, right? So the transition map is something like V prime going to V prime composed with some reparameterization that depends on V prime. So it's again this guy that is usually not differentiable. And so now, again, there's sort of a splitting of paths of polyfold approach and all the other approaches. The polyfold approach at this point just says, let me just change the notion of differentiability so this becomes smooth. And that means we really need to talk about this later. Everybody else just gets stuck here. We don't want to change the notion of differentiable structure, so what do? Well, clearly we can't really use this much here. So we're back to this situation of just having the transition map over a small fuzzy little subset. Right? Well, what we do have is we have this local stabilizing idea. But again, so now also we might choose different stabilizers. And then at least we don't need transition information maybe on this large space, but maybe only on the smaller spaces of sort of maps that are holomorphic up to E, or maps that are holomorphic up to E prime. And so now this is a smooth submanifold, or a smooth manifold of something. So is that. And on some fuzzy subspace of this, I have my transition map. And the idea is, well, to somehow make a larger set of curves that both of these sit in. And that means I ought to have curves that have an error in E or have an error in E prime. And that is some sort of decent notion of transition chart. There's sort of it's not a direct it's not a transition map. It's a transition chart, right? There's a chart that covers the overlap, and some parts of my both charts sort of get embedded in there. I can use that hopefully to glue things together. So that's the idea of a sort of overlap chart. And it has issues. And those issues are very similar to the gluing issues. One issue is that really, let me call this ill-defined map here, capital Phi, then really if I try to make this a little more precise here, I probably should say maybe W in the slice on the left-hand side, but then E prime sits over the slice on the right-hand side. So really what I mean here is I should pull back E prime with that map. And so then I have exactly the same two problems. The second problem is this actually a smooth bundle? Despite the failure of phi to be even differentiable. And the other question is, even before that, an algebraic question, is that actually constant rank? I'm summing spaces here. It's the same question as the injectivity question before here. So, ideally, I guess I'd like the two to not intersect in anything other than 0. So I get, constant rank. So that's sort of on our to-do list when we actually try to make these charts. Questions?
So this sum, we're not thinking of it as a direct sum, we're thinking of it as a sum within this ambient. That's the question of what we should think of as this. Think this as of? Of what should we think of it?
Preview. This has a simple answer. The simple answer is you should not write it that way, you should write it as a stabilization. And then injectivity is not a problem. This here has no simple answer. The answer is again the same, that you need sort of geometrically defined perturbations for this to make sense.
Why do we need smoothness exactly?
Well, at least you'd like differentiability.
Why?
Well, because, so you have two smooth manifolds here that gave you finite dimensional reductions. And you were not able to make a transition map between them directly. So instead, your idea is I'm going to make a chart that covers both.
But it's a given that
and
you
so,
want to make something with a smooth structure.
Well, I want to make this chart, so I should at least make this set here a topological manifold. Right?
Okay.
And so that means what I'm looking at here is I'm solving a d-bar equation up to something. And if I want to solve that the only way I can give this even a topological manifold structure is if I have some kind of implicit function theorem for the equation here.
Okay.
And that implicit function theorems only work for differentiable maps, right? So yeah, that's right. I think that is right, and that is probably a source of a lot of mistakes where you think, okay, I'm only thinking now about transition data between finite dimensional things. And these are all smooth maps, so why do I care about differentiability issues when I do the transition maps? The answer is, you don't have a transition map, you make a transition chart, and when you make that chart, you have the same infinite dimensional Sobolev space setup that you had, that you needed to come up with to make the charts in the first place. So, right, so you need, I guess, what do I want to say? You need sort of slice times E plus phi star E prime to curly E, right, U and some big E to D bar U plus E. So the question is whether that is, at least we need that to be some sort of C1 Fredholm. And hopefully transverse to 0. Because that's what would give this here also structure of a manifold. And so in some sense we would then have a decent sort of overlap chart. All right, so that's just to say I haven't disposed of these problems. They will come back to us again when we talk about overlaps in Kuranishi approach. So just wanted to get this all sort of on the plate and sort of roughly on our radar as we go through the different approaches now. So on Wednesday I'm going to start with a list of guiding questions and places to look for problems as we go through our approaches. I then challenge you to call me out on every time I sweep something like that under the rug.